I would like to ask Iris to share the screen and unmute herself, and good luck with the lecture. I'm curious to hear what you're going to tell us.
Thank you, everyone, for turning out in such great numbers. It's lovely to see. I just had a sneak preview of the attendee list, and it's lovely to see some familiar names on there, especially as this is a really challenging time that we are currently living through, and it's not all that easy with people teaching their children at home and so on, to take the time out to attend something like this. So it's absolutely lovely to see you. I'm also very, very grateful to Martin for inviting me, and for Kelly, of course, to agreeing to come on this and exchange some ideas with me, and Pete Hoekstra as well for reflecting on what we're going to say. So thank you all very much. My talk is entitled Drie Vliegen in één klap. And it's really a vision for how we might achieve the management of coasts, so that the biodiversity, the carbon capture, coastal protection, and also all other ecosystem services that the coast provides us with are retained and enhanced. Now, I'm drawing in this talk on nearly 30 years of experience of working on coasts, initially on coasts more generally, and then I specialised on salt marsh geomorphology particularly. And I want to therefore focus on the function of salt marshes largely as a system component of the coastal landscape. So the conservation of biodiversity, carbon capture and coastal protection is really a given, I suppose, if we manage to conserve and protect these environments into the future, with all the challenges that that brings with sea level rise and environmental change and the human use of the coast. And the reason why that's important is that coastal wetlands at the moment really are not just an integral part of the coastal landscape, but they are an environment that many people depend on directly. They provide the food for an estimated 500 million people around the globe, and an estimated 775 million people actually depend on them directly in some shape or form. They sequester carbon at twice the rate of terrestrial forests, and that's often forgotten when we talk about them. Even though they exist in relatively narrow bands around the coast or in small pockets, actually this is not an insignificant contribution because of the higher uptake of carbon that they can achieve. They also provide the basis for high levels of global biodiversity, even if the biodiversity on the salt marsh itself may be relatively small, but key migratory bird species absolutely depend on these systems as feeding grounds on their migratory routes. In my talk, however, I also want to aim towards another conclusion here, and that's really one where the curiosity-driven science is understood at linking very closely to the applied science of what we do, and is very closely linked also to the monitoring and the management of what we do. And I very firmly believe, through my engagement with this over the last 30 years or so, that these three are equally interconnected. These three flies, or these three birds, these three cornerstones of what we do are very interconnected, and they have to work in conjunction with one another in order for us to conserve these valuable types of coastal habitats and coastal systems. Now, Martin has already alluded to the fact that this talk is a bit more broader and looks at systems in a bigger context, or at least I would like you to have that at the back of your mind. And there are four characteristics of coastal systems that we really must never forget. And that is that they are interdependent with one another. So if I'm talking to you about salt marshes as one example later on, never forget that there's a connectivity between the salt marshes, the tidal flats that bound them. They may contain seagrasses. In the tropics, we may have coral reefs bounding the borders of mangrove areas, for example. They are very complex. They are open systems. They have a boundary that is open. The boundary we place on these systems in our models, in our understanding, is an arbitrary boundary always, and is always time and space dependent. so that the inputs and the outputs into our system that we're studying are also dependent on the timescale that we consider the system over. And last but not least, they are extremely dynamic. And in the picture in the bottom right there, you can see some overwash deposits over the dune fields of Scald Head Island in North Norfolk that occurred during an extreme event. So there are these kinds of environments are punctuated by unpredictable events, and they are often non-linear in that we can't necessarily predict the trajectory of them over time. So it's not unlike the weather in a way when we think about predicting coastal change, and maybe not quite as bad as tossing a coin to see whether it's going to rain or shine, but perhaps we could do worse than take the wise words of Lao Tzu on board, who said that those who have knowledge don't predict, and those who predict don't have knowledge. So there is a kind of element of that we need to keep at the back of our minds as we go through the thinking I'm going to present you with. Now, how do we move on from there? Well, Hope de Vriend, not that, well, maybe it is quite a way ago now, 20 years ago or so, summarized this quite nicely in the project I was involved in on the prediction of aggregated scale coastal evolution, when he said that in summary, we have a nonlinear dynamic system. It's dissipative and with a continuous energy input, randomly forced at a wide variety of spatial and temporal scales, and exhibiting free as well as forced behavior. And that largely arises out of this morphodynamic connectivity we have at the coast, that water levels and waves shape what we see shapes the waves and the water levels, because the topography, it basically constrains the space over which waves and water levels can operate, can move sediments, can move seeds, can move nutrients, and so on. Those are operating on different timescales, and it's not unlike a double pendulum from the science of physics, where you have different kind of oscillations that oscillate with one another, but they force one another also in that process. And as those of you who might know about the double pendulum will already appreciate, if you hold the bottom end of a double pendulum up and you let it go, the trajectory that it will mark out through space, which is illustrated in the little diagram at the bottom there, the light trace, is completely unpredictable to us, because we can't actually pinpoint the initial position of the double pendulum precisely enough to know exactly where it's going to be after a number of time steps. And I would challenge you to see coasts in some way like that, but perhaps take the quote of Hope de Vriend at the top there as encouraging us to look for the forced behavior, but never forgetting that there is free behavior as well that results from this morphodynamic feedback. So the best we can do, I think, is to aim for something that we might call behavior-oriented understanding or behavior-oriented prediction. And that's really what underpins a lot of my own research. And I have a few examples to take you through now on this. But it's really an approach that's based on data and observation, charting geomorphological change, looking at sediment transport pathways, and also, of course, human interventions. And in the little teaser video that we sent, Kelly already asked about grazing on salt marshes, for example. Now, that is a clear forced behavior, but that may well have feedbacks that then become more of a kind of free-flowing repercussion of that forced behavior. So the aim is always for us, I think, to look for the simplest schematization that adequately describes observed behavior. And in doing so, we have now a number of tools available to us. So with respect to salt marshes, for example, we can ask the question as to how rapidly they accrete over time in the vertical dimension. We can ask the question how much carbon they sequester per unit area. But that in itself is of little use if we don't understand how their aerial extent changes over time. And so really salt marshes are three-dimensional systems. And this morphodynamic complexity, this self-organization, rather than just the forced behavior, we have recently exposed that by looking at a real big data application, where we've taken aerial photography images for the east coast of the UK and classified salt marshes into ramped, cliffed, and ridge and runnel transitions towards the unvegetated tidal flat. And then the color-coded categories you can see on that example image on the left there are the different styles of marsh edges or marsh margins. And what we discovered by using Bayesian networks and the application of artificial intelligence methods is that each of the kinds, the morphologies that the salt marsh has at any point in time will have a not insignificant effect on what happens next. So we really are dealing with something where the areal extent is not just a function of a rise in sea level or a function of the wave climate at that point in time, but really of a history of events that have shaped the morphology, and the morphology then drives the process. And with that, I want to take you to another example here that illustrates the importance of looking at different scales over time. So my own specialism has very much been looking at salt marshes as a coastal protection feature. And when I think about that now, after all these years of research, I really have to remind myself always that salt marshes have lots of different scales. So you can have an individual wave acting over a salt marsh that interacts with an individual plant, or you can have the tide come through a complex creek network, flood the salt marsh, and then drain that salt marsh. And the processes of dissipating that energy, dissipating the tidal energy or the energy of individual waves, are seated at different spatial scales within that. So when we look at wave dissipation, that's a great example for me to illustrate to you how this three-pronged interaction between blue skies thinking or blue sky science, applied science, and then the management and monitoring needs to work together in order for us to find answers. So the process of energy dissipation is really relatively simple. It's that the salt marshes become inundated by water, and the roughness elements then take the energy of that water out, whether that's waves or tides. And it's very nicely illustrated in this little video clip here of James Tempest, one of my PhD students. If you just have a flume and you drain the water like that, you can see that the plants bend over slightly, these Spartina swords in here, but that the water level is held back significantly on the upward side of them. So there's a lot of roughness in the system there. And that roughness actually originally was already discovered 30 years ago, and nobody really thought about these systems as coastal protection features at that time. And it was discovered by monitoring water levels in creeks. And you can see on this plot here on the left-hand side, as you go up the plot, up the y-axis, the water level rises. And then as the line crosses that horizontal green line, that's the height of the marsh surface, you suddenly get an acceleration into the negative, that's the flood flow, and then the water level rises some more. You get an equilibrium at the top as the tide reaches its full height, and then the draining of that tide outward. On the ebb tide, you can really see how the water there is held back and drains a lot more slowly until the water level subsides beyond the height of the salt marsh surface, and then you get this hydraulic pulse happening as the efficient creek system allows that water to drain out much more rapidly. Now, that already indicated to us that the roughness of the surfaces of salt marshes is very, very important. So there's that velocity pulse overspill, and there's the high friction, low flow velocity part of this curve. And out of that really just emerged a curiosity question, and that was whether waves traveling over a salt marsh would actually lose some of their energy when they did so. And so in the mid-90s, we were really the first to implement some measurement stations on a marsh in North Norfolk. And at the time, we were working with slightly less advanced technology than we did now. So this is challenging work that then needs to happen. But it proved worthwhile because we were able to then plot the waves traveling across a tidal flat without vegetation. And those are the open diamonds in this plot. And then to plot the dissipation of waves over the vegetated salt marsh for comparison. And those are those those black dots in this diagram. And there's just one other thing to note that's a bit quirky here, and that's that the energy loss is greater towards the bottom of the diagram and less high towards the top of it. So we were able to have enough data here through very detailed, very time-consuming observation, but very worthwhile because it allowed us to have a direct comparison in a natural setting between the unvegetated tidal flat and the vegetated salt marsh. And you can see here that the dark dots, the black dots, are all plotting underneath the open diamond. So there is clearly something happening here in terms of the effectiveness of the salt marsh with the vegetation on top and taking the wave energy out. Now you'll see also here that the water depths are relatively small. They're all less than 1.4 meter on the x-axis here. And so that then really raised the question as to what happens during a big storm event, which is when we really need to know what happens. So we entered into a long time period of additional measurements, trying to capture that storm. We took better equipment and more refined digital techniques with solar charged data loggers and so on. And we took them out onto the east coast of the UK, where we thought perhaps we can capture a storm more readily. And we also placed a lot more of these wave sensors in a cross-shore transect on a rough bed so that we could isolate vegetation and bed roughness effects and so on. And that again was very successful. And you can see on this diagram on the right, the waves coming in from the open North Sea. And then on the left, you've got the seawall, and the x-axis is the wave heights. And you can see how they are reducing as the waves are moving over the marsh edge, which is that green band, vertical band in the middle, and then reducing to pretty much nothing after only 130 meters of salt marsh. Now, we then collected more data, and we managed to get waves that were about 90 centimeters high over the tidal flats. But by no means was this ever capturing a real storm surge. And then at this point, we started to talk about ecosystem services. People started to talk about the coastal protection of salt marshes, coastal protection reduction as a result, as a result of salt marshes. But the data we had was all in shallow water depths. So the application kind of caught up with the science. And we then felt the pressure that we would have to make the science, in a way, fit the question better. So we started with really blue skies science, and it was then taken up by policy and by the engineering communities. And we thought we're going to have to answer that call. So it became a little bit more applied, and we then went and looked specifically for storm surge settings. We took the equipment to the Baltic. And in the Baltic, we know that storms are common, meteorologically forced storms are common. We were also quite interested in the different vegetation types over there. So we implemented the same sort of techniques. And again, we got some data, and you can see that plotted on the right-hand side there, where the energy reduction decreases with an increase in water depth. But again, we didn't really catch a really extreme event until it happened. And then it destroyed our instruments. So you have this real sort of story of evolution of the science, answering some of these applied questions. And then, of course, the only thing we could do is bring the salt marsh to the storm surge if we can't get the storm surge to the salt marsh when we're there, and record it. And so we were very fortunate that we were then able to bring this into a laboratory setting. We excavated quite a lot of salt marsh of northern Germany, and we're very fortunate getting the permission. Don't worry, we didn't really destroy the entire nature reserve. We only excavated 200 square meters of it. We put it in the large wave flume in Hanover. And with that, we had the opportunity, with a 7-meter deep flume, we had the opportunity to construct a 40-meter long test section. And that looked roughly like this, where a second in this video is an hour in reality. And it was a lot of effort, but we were really able then to get to a situation where we could explore this forced aspect of what is such an unpredictable system. So we took this controlled environment to isolate this very individual, very specific question about high water levels and the efficiency of wave dissipation by salt marshes in those conditions. So when that was all done and we filled the flume with water, we were of course extremely concerned that the whole thing was going to float to the top and the entire effort would be ruined. We had a few mice float to the top, but the salt marsh itself stayed down. And so after we'd rescued the mice, we then were able to do our measurements. And the measurements were really very interesting to me because I knew that the salt marsh was efficient, would be efficient in taking some of the wave's energy out, but I had not expected that in under 2 meters of water depth above a salt marsh, wave heights of around 20 or 30 centimeters. So that's really quite small if you try and visualize that. So it's the size of the room that you're sitting in with maybe, you know, one of those rulers of a wave height on top of the surface of the water. So the dissipation of the wave-driven orbital currents to the bed is really quite high in those conditions. But even so, regardless of the wavelength that we used, and we were only looking at non-breaking waves at this point, so there's no dissipation due to breaking, we saw that the reduction in the wave height was between 15 and 20%. Sorry. And when we mowed the test section, it was reduced by about 60%. So the plants alone were responsible for 60% of the reduction in the wave's energy. So that then led to the next question. So here you have an example where the application, the question, the applied science application then led to another question that really kind of linked on from that, and we kind of stayed very much in the applied field. And that was whether the salt marsh itself would be destroyed in the process. And so we measured the elevation of the surface with these very precision pins, and then plotted the results of that. And we could see that the elevation change was very, very small, first of all. So we had a millimeter order of magnitude surface elevation change as a result of this surface being exposed for a couple of weeks to storm surge conditions. And we also saw that a particular plant species, the P here in this top right-hand plot, stands for Puccinellia. And that's a plant that grows very, very densely together, puts dense roots out, and therefore stabilizes the surface adequately to protect it from erosion under these extreme conditions. So we then went back to our blue skies thinking and went back to all of the theory around how salt marshes build over time, how the soil volume is a function of plant processes, of sedimentation that comes in with the tides, of autocompaction of the surface and so on. And you can then start to ask really interesting questions about the importance of different types of plant species for the longer term evolution of salt marshes. So bringing this up into the longer term again, we then have to remind ourselves that these systems are not just forced, but also slightly unpredictable, and they become unpredictable, particularly through the influence of storm surges. And those are, of course, meteorological events. And when storm surges move over complex nearshore bathymetry, for example, on the east coast of the UK that you can see in this plot on the left here, they manifest themselves very, very differently over salt marsh environments along the coast. And so we went along the coast of the east coast of the UK after the 2013 storm surge. We mapped the impact. We saw how complex it was. We knew that the nearshore bathymetry was complex. We then went out and we surveyed the drift lines that were left behind to very precisely pinpoint the height of the wave energy and the water levels. And we saw as a result of that how important the existence of salt marshes is, not just for individual waves moving over 40 meters in a wave flume, but actually for mediating and moderating the water levels that are encountered at the coast relative to water levels that might have been predicted. So the Environment Agency predicted 4.86 meters of water levels on at the high water mark of this coast throughout the North Norfolk stretch that you can see on this map. But in our measurements, we could see that actually the configuration of tidal creeks and salt marshes could change that from anything less than 1.82 meters below that level to plus 1.4 meters above that level, just as a result of this morphological complexity near the coast. So there is a number of questions that arose from that, and that took us then more towards the kind of blue skies research thinking. And one of them was that we observed a number of different mechanisms of failure, not just of the marsh margins themselves, but of the coastal defences, of course. And it occurred to us that really nobody asks the question as to how stable salt marshes are. We might ask the question how stable an embankment or a dike is, a flood dike, but not really how stable a salt marsh is over time. And so we then turned to again, quite modern technology and used X-ray CT scanning instrumentation to look underneath the soil and to start to look at the root densities and the complexity of roots below the ground and how that might mediate and moderate erosion under different water level conditions. And you can see that quite nicely in the top right here as the dense root mat that holds that surface together becomes undercut through the waves and tides. And so this research kind of started to bring a few strands together. You remember that I mentioned that Paxonelia was very good at avoiding erosion. Paxonelia also tends to be very good at binding the surface together, but then it tends to be undercut if the water level happens to be more frequently underneath the level of the roots. And we also then ran an experiment with enhanced CO2, to which we exposed Paxonelia as well as other salt marsh plants. And we found that if we grow Paxonelia for a season in these controlled pods that you can see at the top of the diagram there, that Paxonelia itself is actually one of the best salt marsh plants out of the set that we looked at in terms of influencing the growth of the surface of the marsh on which it grows as a result of elevated CO2. So here we come again, a very blue skies question that we became interested in, but actually it has an enormous application because under sea level rise, salt marshes are very threatened. We've seen an acceleration in sea level rise from 1.4 millimeters in the early 20th century to 3.6 millimeters per year in the more recent times. And salt marshes are, of course, only persistent if they can keep up with that rise. So not only do salt marshes or coastal systems in general exist at this interface between a hugely complex number of forcing factors that will drive the system. It has its self-organization, but it's also driven. And so we need to be very mindful of the complexity of that, but also there are individual aspects we can isolate of the system, that are perhaps better at coping with these stresses than others. And this slide in here is really just to remind you that it's not all about sea level. There is a number of other challenges, not all about sea level and not all about CO2 concentrations, but there are also terrestrial challenges of increased runoff, and then there is the potential of increased storm frequencies from the seaward side. So again, this kind of takes us back to where we started, that the system is a system that we can study in terms of its response to forced conditions, but we have to keep in mind that the whole of the system is much more complex than an individual forced response. And so I want to end really by just making a suggestion for our discussion. And Kelly asked in the teaser video about carbon sequestration of salt marsh, and that's clearly something that will be very important in the Wadden Sea. And it got me thinking as to whether a schema that we developed for coastal protection could not also be applied to the way we think about carbon storage, in that with coastal protection, we've started to think about wetlands, coastal wetlands, as an element of risk reduction. So if you want to reduce the risk of flooding, you start by having perhaps a green buffer zone of a salt marsh. Then you have to still rely on some form of levees or flood protection. Then you need some building codes, and then you need to make sure that any individuals, people who are, or communities who might still be at risk, can be evacuated in time. Whether we can now think about all of the ambitions we have in terms of conserving salt marshes for ecosystem services in a similar kind of way, so that we think about what is the lowest common denominator we can actually work on in order to increase or enhance carbon sequestration. Is it building the aerial extent of salt marshes, or is it doing something else that allows more carbon to be sequestered within salt marsh, to ensuring there's enough sediment supply or whatever? And then we kind of think about the next important and the next important and the next important step until we absolutely maximize each and every one of the ecosystem services, while also being mindful of the fact that, in that process, we might be trading off one against the other. I think, in conclusion, we can restore and conserve salt marshes for biodiversity, carbon storage, and flood defense, but we can only do that through a combination of research in which we understand the general principles, where we do focused force response kind of experiments. But we need to then, in order to apply it to a detailed site-specific, situation, we need to do observations and monitoring at individual sites. We cannot get around that because of the complexity of the system. So just as coasts are nonlinear systems dominated by feedbacks, we need our management to be dominated by feedbacks, effectively, between observation and action and intervention. Thank you very much for listening.
Thank you very much, Iris. That was fantastic. I propose that all attendants, if they have any questions, now share them in the chat. And while they do so, maybe already there is a question. Maybe Kelly already has a question right now.
Yes, well, I was really thinking about, first of all, thank you, of course, for your talk. It was really interesting. You showed us the three-dimensional, or how to look at marshes three-dimensionally, and so you showed these nice pictures of different edges of the salt marsh, and you saw one of them that showed sort of these ridges or these fingers. Do you think that type will actually turn into a cliff, or so? How do you think that will develop in time?
Yes, so it was a very interesting discovery that cliffs are actually over the timescale. So this is a decadal timescale that we took to look at these. So again, we have to be kind of really mindful of what timescale we're looking at these systems. But over the decadal timescale, it was actually the ridge and runnel systems that tended to erode. All of these were erosional as well, is what I should point out here. But the ridge and runnel erosion tended to happen most rapidly and not actually turn into a cliff. No, it just seemed that there's a kind of process by which the runnels become widened and then incised back into the marsh, and the cliffs actually turned out to be almost the most stable over the timescale over which we looked at them, which was interesting because I expected them to perhaps be retreating the fastest over time. And the ramped transitions were sort of in between the two. So there's not necessarily a flipping that we observed over the time that we were there, but a bit of an indication that that there is a sort of a ridge and runnel transition towards a ramp that might then turn into a cliff. So those are still very preliminary kinds of results. But the interesting thing was that there was a measurable correlation between the morphology we had and the speed with which it was retreating over time. even when they're very close together and exposed to the same forcing conditions.
Okay, very cool.
Right. For anyone who has a question but cannot access the chat, you can also try and send me an email, and as a matter of exception, I'll now open the floor to someone who's raised a hand. Nice try, Mick. Maybe come in, open your camera and your speaker and microphone, and phrase the question, please.
Yes, well, thank you. I was maybe a little bit rude here to raise my hand, but in the absence of the chat, thank you for your presentation, Iris. Very broad question. How should we manage salt marshes under anticipated sea level rise?
Yeah, very good question. I mean, at the moment, it is looking like sediment supply is absolutely critical, of course, to salt marshes. So the first thing to do would be to make sure that there is an adequate supply of sediment to the salt marsh system in question. So again, you know, this is we can take the general findings from some of the more blue sky science that is out there, and we can then try to apply that to a particular location. But sediment supply is absolutely critical. Once you know that you have enough sediment supply to a salt marsh, then the next question becomes what happens at the seaward front of that salt marsh, and also maybe in terms of the management of the salt marsh, you know, is it a grazed marsh or not? Because as Kelly will know and will maybe tell us a bit later, I don't know, but about, you know, grazing will have an effect on salt marshes as well, and also will affect the way in which they might be able to keep pace with sea level rise. So there are management questions that will need to be looked at, but also then in the transition towards the tidal flat, ultimately with sea level rise, the whole of that transition needs to be looked at. So the waves will form, waves and tides will form and influence that coastal transition from deep water across the tidal flat to the salt marshes, or through the estuaries in the channels to the salt marshes. So river flow might be important depending on the setting of the salt marsh. And so it may well be that sea level rise is a relatively small threat to an individual marsh. And some of the global studies have shown that that in fact is the case, that globally the biggest threat is the reduction in sediment supply. So it would need to be an approach that's, you know, very context aware and very site specific.
Okay. Nice answer. Thank you.
Right. I do get a feeling that not many people actually have access to the chat, so do feel free to email me your questions. There's one email arrived here that is actually the suggesting that the entire Netherlands are in your high-risk zone right behind the seawall, which leads to one question I had. So what if we wanted to preserve the carbon stored in these salt marshes? And we're talking about shifting salt marshes and a coastal squeeze and all that. Isn't the bit where the salt marsh is shifted away losing the carbon? Isn't that a problem that we are facing? Should we not perhaps try and protect the salt marshes against erosion on the seaward end as well, and they shouldn't be able to shift?
Yeah, good question. I mean, again, that's ultimately a question of the coastal configuration and the availability of sediment supply. You know, if we could, and you could make sure that it's not impossible for salt marshes to build seawards under conditions of sea level rise. So the erosion is kind of somewhat separate from the concern of sea level rise. Sea level rise may cause erosion, but it may not. If there's enough sediment supply, and if the conditions are such that the sediment can settle and be retained, then yes, it would of course be preferable if we can not lose those marshes. My worry would be that we would need to look very carefully as to the methods that we use and make sure that we don't shift that problem down for generations. That's often, I think, one of the problems we've had with coastal management approaches in the past, is that it's relatively easy to solve a problem over the next 10 or 20 years, but we might then make it a lot more difficult to solve after that. And so it might be better to think about letting some erosion happen, but then think about whether we can actually create new carbon stocks or stores elsewhere where we know that they are more sustainable, for want of a better word, that they're more long lasting, and that we don't then end up with a bigger problem in 20 years' time.
I have a funny feeling. I think my crystal ball says that Piet Hoekstra will also talk more about this. But for now, there's 2 questions coming through the chat and the email. And the first question in the chat is by Emmanuel Duits, and he asks, what is the cause of this reduced sediment supply? And maybe answer that first, and then I'll get to the next question.
What is the cost of the reduced sediment
supply? The cause of this reduced sediment supply.
Oh, the cause. Sorry.
Yeah.
Yeah. So it's largely us interfering with river systems. So it's the embankment of rivers. It's the great example is the Mississippi Delta, of course, where you can really see, if you look at Google Earth images of the Mississippi Delta, you can see how the delta is reduced really just to a channel that is encased in dikes, and the land around it has sunk and subsided and is now all waterlogged. So that you have this kind of bird's foot image of a delta, which is not what a delta should look like. So it's the fact that the rivers have been prevented from flowing freely and delivering sediment freely to the coastal zone. And where sediment is coming down the rivers, it is often ending up in deep water rather than being distributed along the shore. And the other cause, of course, is the protection of cliffs, coastal sedimentary cliffs that are that were eroding and that we decided to live on top of, and then that requires us to protect those cliffs, and the sediment delivery to the coastal system is reduced. Another issue that has come up recently is that for some coastal systems, the rate of sea level rise is such that we can foresee that the action of the waves on the seabed that usually transports material either along the coast or towards the coast, it may be reduced as a result of a deeper water level, and therefore you have less sediment that makes it into the areas that previously benefited from a lot of sedimentation. There's multiple different reasons, again, really depending on context. And I think that's why it's so very important for us to do the regional and local monitoring that, efforts that we need to do in order to establish what the reasons are in any given location. It could be any combination or a multiple of those reasons.
Right, and more about sediment supply and the effects on large coastal plains and deltas in one of the breakout sessions by Jana Cox and Jaap Nienhuis. There was also a question in the email from Ton Hoytink. Can salt marshes be recreated just like that? How many artificial salt marshes exist and function properly?
Yeah, again, another very, very good question, and I could give a whole lecture on that. That would be quite interesting. I've moved to Ireland from the UK not so long ago, and in the UK, of course, we had the first mandatory alignment site in 1995, and everybody was very excited by that when that started. And then all the questions started to emerge as to, can you actually break a dike or an embankment and recreate a salt marsh on something that was on a piece of land that was in agricultural production for decades? And we then discovered that actually the agricultural activity on that land had obviously modified the soil structures, compacted the soil, lowered the elevation, and then to open that area up to tidal exchange, to the delivery of sediment into that area. Yes, it will lead to some sort of sedimentation. Yes, it'll lead to some vegetation colonization, but it looks as though it can take hundreds of years for that kind of system to then really develop into what we might think of as a functioning, natural, in inverted commas, salt marsh system. So we can restore something that contains salt marsh plants, that that manages to survive and maintain itself, and but it will take time before the history of human intervention sort of gets lost within the system, and you then have a natural creek system that functions well, and you have a salt marsh that has the highest diversity it could have, or the highest carbon storage it could provide, and so on. So I think it's a really good question, and I think that's why a lot of research is now needed to look at what we can do when we restore to make sure that the restoration has the best chance of being as effective as possible in getting a system that functions properly.
But nevertheless, your answer really is that if there is a natural salt marsh, we should really try our best to preserve that, because recreating that is going to be a lot of trouble. And the next question relates to this by Dov Korenblit. He asks, is there a relation between the functional plant diversity and geomorphological resistance or resilience of coastal landforms?
Oh, brilliant question. Yeah. So this is something we're working on, a project at the moment called the Resist project, which is a leftover project of mine that I left in the UK, but I'm still involved with. And that's exactly what we're looking at there. We had 4 different plant species, and we're looking at the comparing the different root systems of these different plant species and their effect on the soil stability. It is looking like that it's a combination of the plant species and their roots and the properties of the sediment in which the vegetation grows. So I wouldn't be surprised if we find over time, and this is really me just speculating, that also these kinds of feedbacks that we found for Paxinellia, for example, where CO2 fertilization led to an enhanced growth and below ground root production, that that ultimately will have a feedback into the stability, because when you get more organic matter, for example, underground, that does tend to have an effect on the soil stability. So those are really good questions, but I don't have the answer as yet, but we're working on it.
Yeah, and I also know there's an older paper by Martin Skov, whom we all know well, and he's measured erodibility of the soil under different densities of vegetation, and the denser the vegetation, the more species there actually are, and the more resistant it is against the erosion. So there's at least some experimental evidence pointing in that direction.
Yeah, whereby I think one of the questions we've asked ourselves a lot, and this will be something really interesting to discuss later on in our discussion groups, is what resistance we're actually interested in. How do you test for what is the force against which we are interested in the resistance, if you see what I mean?
Yeah, no, absolutely. There's one final question in the chat by Pella Adema, and he asks, how do you think policymakers think about salt marshes in terms of coastal protection, and do they deem it an important component, or does it not receive much attention? And how does this match with what you think?
Yeah, it's taken a long time. Yeah, it's taken a very long time. I mean, I think if I had to say one thing about my career so far, it's just the immense amount of time it's taken from working on something and finding the evidence for something, and for that then to make it into policy. And I think we're probably the next generation now coming into science is a lot better at communicating the science to policy, and I think maybe that pathway will be shorter. But in my experience, policy is still not quite there in recognizing the science that we have on this. The science is very clear that it does pay off. It has actually a financial benefit if you have a green buffer zone in front of your embankment or dike. But to implement that is another challenge, and it's of course also, it raises very, very uncomfortable questions in that, you know, in order to create that green buffer zone, and these, we've sort of talked around these in the questions just now. You know, sometimes it may actually mean that we will have to move people landwards to restore a functioning coastal buffer, and that is, of course, politically a very, very difficult thing to discuss. And so it's maybe not surprising that policy is a little way behind.
Yeah, that's exactly the same in the Netherlands, especially in the southwest. There's a lot of resistance to the idea of opening up some areas to flooding. And the very final question in the email about this point is by Richard Marijnissen, and he asks that given flood protection standards, they allow only a flood in at least once every 1,000 to 10,000 years. This used to be the case by law in the Netherlands, actually. So we're only looking for extreme cases in the Holocene, and only those are allowed to flood the Netherlands, at least in theory. So he asks, what would a marsh look like in a 1 in 10,000 year condition?
If it was flooded, I'm assuming, yeah, so if the marsh was flooded under that kind of event. Yeah,
the storm surge plus storm waves and the whole shebang.
I think it would be absolutely fine. It would be so fun. It would, you know, that would be my, based on the science we have, that would be what I would say. That kind of event will last, you know, what, a few days. It will be, you know, it'd be deeper water than we generated in the Hanover wave flume. So the impact on the vegetation on the bed will be much less, or at least it'll be comparable. The waves might be bigger as well, but the water depth will also be bigger. So the stress on the bed will likely not be any less. We really pushed that situation in the Hanover wave flume, in that we tried to get the waves as big as possible for that water depth in order to create the absolute maximum stress that we could get at the bed. And we could see the plants responding at the bed and moving around. And they didn't take, you know, that storm that we generated lasted almost a couple of weeks. Now, a storm, even a 1 in a 10,000 event, would probably not last that long, you know. So I think it would emerge, and you would have a lot of biomass on the coast, which would be the dead stems and leaves that would have accumulated on the surface of the marsh. They would all float to the top. They would all be floating landwards. And this was an interesting side effect of the 2013 storm surge. The roads and the infrastructure was buried in debris, but the marsh was actually fine. The marsh will recover, and it won't, you know, take that hit necessarily.
Right, yeah. And that is probably also going to depend a lot on the morphological conditions, because if, like in the Netherlands, we have subsided Netherlands, a big dike in between, and a raised marsh, and then a deep area, and then the dike breaches, then you get a tidal floss across the marsh, and then you get serious erosion. But that's a very peculiar setup that we've made for ourselves here the past 1,000 years.
Yeah, and again, that illustrates how important it is to look at the specific context and the specific setting.
Yeah, right. We've come to the 3 o'clock, which means we're going to have a brief break. That means I'm going to stop the recording, and we'll be back for the lecture by Kelly exactly at 5 o'clock, 14 minutes past 3, and then I'll switch on the recording again. Thank you all for attending. Now it's time for a brief break.